Welcome to G-Fun Facts Online. Today we're talking about cosmic cannons firing right here in our own backyard. For decades, when astronomers looked for the source of the most energetic particles in our galaxy, they pointed to the biggest explosions imaginable, the death of massive stars, called supernovae. But a flood of new evidence has revealed a new suspect, a smaller, stealthier, and shockingly more powerful type of engine. They are called microquasars, and they have stolen the title as the Milky Way's most extreme particle accelerators. At its core, a microquasar is a binary star system with a violent secret. One star is normal, like our Sun, but its partner is a compact object, either a neutron star or a stellar mass black hole, the dense corpse of a long-dead star. In this deadly dance, the immense gravity of the black hole, or neutron star, tears gas away from its living companion. This stolen material doesn't fall straight in. Instead, it forms a swirling, superheated structure called an accretion disk. As gas spirals inward, friction and pressure heat it to millions of degrees, causing it to glow intensely in X-rays, which is how we first find many of these systems. But the accretion disk isn't just a glowing swirl of doom. It's the engine that powers the microquasar's most spectacular feature, a pair of relativistic jets. Perpendicular to the disk, powerful twisted magnetic fields grab a fraction of the inflowing material and funnel it into two tightly focused beams of plasma. These jets are then shot out into space at speeds approaching the speed of light. It's inside these jets that particles are accelerated to unimaginable energies, turning the microquasar into a galactic cannon. The name microquasar is a nod to their much larger relatives, quasars. Quasars are the blazing cores of distant galaxies, powered by supermassive black holes, millions or billions of times heavier than our Sun. They also have accretion disks and jets, but on a colossal scale, stretching for millions of light years. Microquasars are just scaled-down versions. A quasar's disk might be 1 billion square kilometers wide. A microquasar's is a mere 1,000. But this size difference is a huge advantage for scientists. Because the physics in a microquasar happens on much shorter timescales, we can watch changes in days or even minutes that would take thousands of years to happen in a full-sized quasar. This makes them perfect cosmic laboratories for studying the fundamental physics of how black holes feed and launch jets. The story of their discovery began in the 1960s with the identification of objects that were strangely bright in X-rays, known as X-ray binaries. The real breakthrough came in 1979 with a peculiar system named SS-433. Astronomers saw it was spewing jets of matter at an incredible 26% of the speed of light. This was the first time such relativistic jets had been seen from a star system in our galaxy, and SS-433 became the prototype. But for a while, it was considered a one-off freak of nature. Then, in the early 1990s, the picture expanded. In 1992, the Very Large Array Radio Telescope saw a source near the galactic center with double-sided radio jets that looked just like those from distant quasars. The term microquasar was coined for this discovery. Just 2 years later, another object, GRS 1915+105, sealed the deal. Observations in 1994 revealed something that seemed impossible. Blobs of plasma in its jets appeared to be moving faster than the speed of light. This phenomenon, called superluminal motion, is an optical illusion. It happens when a jet is moving very close to light speed and is pointed almost directly at us. Discovering this in a galactic object was stunning confirmation that these jets were truly relativistic, drawing a direct parallel to the physics of giant quasars. GRS 1915+105 also became famous for its extreme, chaotic variability, giving us a real-time window into the turbulent relationship between the accretion disk and its jets. These discoveries laid the groundwork for a new field of astrophysics, showing that the same engine, an accreting black hole, powers both the small and the colossal. The power of a microquasar is all about accretion. The behavior of the accretion disk can change dramatically, leading to different states. In the hard state, the accretion rate is low. The inner disk is a hot, thick, transparent flow of plasma. This state is marked by a strong, steady radio jet and high-energy X-rays. In contrast, the soft state happens when the accretion rate is high. The inner disk becomes thin and opaque, and it extends much closer to the black hole. In this state, the powerful jet is often suppressed or quenched. The transition between these states is still being studied, but it's clear the jet's power is tied to the structure of the inner disk. It's believed that in some systems, like the famous Cygnus X-1, as much as half of the energy released by the accretion process is channeled directly into launching its jets. The launching mechanism itself is thought to be a magneto-hydrodynamic process. Imagine magnetic field lines anchored in the rapidly spinning accretion disk. As the disk spins, these field lines get twisted up like rubber bands, building immense magnetic pressure. Eventually, this pressure flings plasma outward along the black hole's axis of rotation, creating the jets. The spin of the black hole itself may also contribute a significant amount of energy to this process. So how do these jets become cosmic particle accelerators? The primary mechanism is believed to be diffusive shock acceleration. As the jet plows through the interstellar medium, it creates powerful shock waves. Charged particles, like protons and electrons, get trapped in the turbulent magnetic fields around these shocks. They are then bounced back and forth across the shock front, gaining a bit of energy with each crossing. After countless bounces, these particles can be accelerated to near light speed, reaching energies of peta-electron volts, or PeV. A PeV is a quadrillion electron volts. For perspective, that is thousands of times more energetic than anything we can achieve at the Large Hadron Collider on Earth. Once these particles are accelerated, they radiate energy that we can detect. This happens in two main ways: leptonic and hadronic processes. Leptonic processes involve light particles, mainly electrons. These high-energy electrons spiral in the jet's magnetic fields and produce synchrotron radiation, which we see as radio and X-ray light. They can also collide with low-energy photons and boost them to gamma-ray energies through a process called inverse Compton scattering. Hadronic processes, on the other hand, involve heavy particles like protons. These relativistic protons can collide with other protons in the jet or in surrounding gas clouds. These collisions create unstable particles called pions, which quickly decay into gamma rays and neutrinos. Distinguishing between these two processes is a huge goal for astronomers. If we can prove hadronic acceleration is happening, it means microquasars are not just electron accelerators. They are factories for cosmic rays, the high-energy protons and atomic nuclei that constantly rain down on Earth. The detection of neutrinos from a microquasar would be the smoking gun for hadronic processes. For most of the last century, the prevailing theory was that the bulk of our galaxy's cosmic rays came from supernova remnants. And while they are definitely powerful, both theory and observation have suggested they struggle to accelerate protons to the highest energies we see. For nearly 70 years, astrophysicists have puzzled over something called the cosmic ray knee. It's a sharp drop-off in the number of cosmic rays detected with energies above about 3 PeV. This knee is thought to mark the maximum energy that the main galactic accelerators can produce. The fact that typical supernovae can't quite reach this energy created a major gap in our understanding. This is where microquasars have burst onto the scene. Recent discoveries, especially from the Large High-Altitude Air Shower Observatory, or LHAASO, in China, have provided compelling evidence that microquasars are pevatrons, natural accelerators capable of pushing particles to PeV energies and beyond. LHAASO has systematically detected ultra-high-energy gamma rays from at least 5 microquasars, including SS-433 and Cygnus X-1. The energies of these gamma rays are so high, they could only be produced by parent particles accelerated to PeV energies, directly implicating these systems as PVatrons. In the case of SS433, LHAASO detected these gamma rays coming from a region where the microquasars' jets are smashing into a giant cloud of atomic gas. This strongly suggests that protons accelerated in the jets are colliding with the gas cloud, producing gamma rays through hadronic processes. This makes SS433 a prime candidate for a cosmic ray factory. Even more striking are the observations of a microquasar named V4641 SGR. LHAASO detected gamma rays from this source, with energies extending up to 0.8 PeV, with no sign of a cutoff. This suggests the parent particles were accelerated to energies well beyond 10 PeV, making V4641 SGR a super PVatron. These discoveries have caused a paradigm shift. It now seems likely that supernova remnants produce the bulk of cosmic rays at lower energies. But it's the powerful jets of microquasars that are responsible for the most energetic particles, those at and beyond the cosmic ray knee. This finally resolves a long-standing mystery and establishes black hole jet systems as a major source of the most extreme particles in our galaxy. Our understanding has been built on a few key systems, a real rogues gallery of cosmic powerhouses. Let's revisit them. First, SS433, the original. Located 18,000 light-years away, its most distinctive feature is its precessing jets. Like a wobbling spinning top, its jets trace out a cone in space every 162 days. It's embedded within a huge supernova remnant called W50, and the interaction between its jets and this remnant creates vast lobes of emission that have been studied across the entire electromagnetic spectrum. Then there's Cygnus X-1, one of the first and most convincing black hole candidates ever found. It's a persistent source, meaning it's always on, unlike many others which are transient. Its black hole is about 15 times the mass of the Sun and is steadily feeding from a massive companion star. Gamma-ray emission from Cygnus X-1 appears to be linked to its hard state when its relativistic jet is active and strong. Of course, there is GRS 1915 plus 105, the microquasar king. It's known for its wild variability and the first discovery of superluminal motion. Its black hole spins at an incredible rate of at least 950 times per second. The system flips between different states, with its X-ray output oscillating wildly on timescales from seconds to hours, directly linked to the ejection of superluminal plasma clouds. And finally, V4641 SGR, the system that was recently catapulted to the forefront of high-energy astrophysics. LHAASO's detection of near PeV gamma rays has identified it as a super PeVatron, a source capable of accelerating particles to energies far beyond the cosmic ray knee. Recent deep radio observations have revealed a giant bow-tie-shaped structure around it, likely the scar left by its powerful jets interacting with the interstellar medium over long periods. The study of microquasars is now entering a new era. The upcoming Cherenkov Telescope Array, or CTA, will be a game-changer. With its unprecedented sensitivity, it will map the gamma-ray emission from these jets in exquisite detail, pinpointing the exact locations of particle acceleration. It will be able to react to transient events in real time, capturing the moments just before and during a jet launch. This will be crucial for testing our models. The other frontier is multi-messenger astronomy, which combines information from light, neutrinos, and gravitational waves. A simultaneous detection of a neutrino burst with a gamma-ray flare from a microquasar would be the ultimate proof of hadronic acceleration, cementing their role as cosmic ray factories. Even with all this progress, major questions remain. What is the exact mechanism that accelerates particles to such extreme energies? What determines whether a jet is dominated by electrons or protons? How exactly is the power of the accretion disk and the black hole's spin channeled into the jets? And what is the full contribution of all the microquasars in our galaxy to the total cosmic ray budget? The journey to understand these objects has taken us from spotting a few odd stars to realizing our galaxy is filled with compact, powerful particle accelerators. These miniature quasars have not only opened a window into the physics of their supermassive cousins, but have forced us to rethink where the most extreme particles in our own galaxy are born. They are a profound reminder that even the collapsed, dark remnants of stars can create phenomena of astonishing power and light. Thanks for tuning in to G Fun Facts Online.